Hello, my name is Caleb Covington, and this is my ME575 designed to manufacture digital tools material selection 2 sustainability presentation. The topic of my presentation was mollusks. The research study I was assigned was Bioinspired approaches for optimizing the strength and toughness of graphene-based polymer nanocomposites. The authors are listed below, and it was published in the Journal of Material Chemistry, Volume 22 in 2012. The scope of this study was the effect of biomimetic concepts on optimizing the toughness and mechanical strength of polymer composite materials. The key question asked to address was how does the implementation of Bioinspired. This review paper used multiple different models because of the multiple studies, but all models used were some form of graphene nanosheet-based nanocomposite sheets. Material performance indexes used for tensile strength, Young's modulus, fracture strain, fracture toughness, and modulus of rupture. And the materials surveyed were graphene oxide sheets, graphene oxide papers, graphene nanosheet polyurethane, graphene nanosheet nanofibrillated cellulose, and reduced graphene oxide and single-walled carbon nanotubes. One study from this research review paper aimed to answer how will the treatment of graphene nanosheet-based nanocomposite paper with engineered D-block protein affect the mechanical properties compared to untreated paper. The engineered D-block proteins in the study aid in the dispersion of graphene nanosheets in aqueous nanofibrillated cellulose solution and improve the load transfer from graphene nanosheets to nanofibrillated cellulose. Also, as we found in the study, this improved synergistic toughness mechanisms. The graphs below, E, G, and F, display the Young's modulus, ultimate tensile strength, and work of fracture for treated sheets of varying weight percent graphene nanosheet. We compared these results to untreated sheets, and all treated sheets showed improvement of mechanical properties and toughness mechanisms. But as the weight percent of graphene nanosheets increased for treated papers, the material indexes used didn't always show improvement. This indicated the key conclusion that considerations of the synergistic effect between different nanoparticles must be made in addition to interface design to create an effective balance between strength and toughness of graphene nanosheet-based nanocomposites. Another study reviewed in this paper aimed to answer how the incorporation of carbon nanoparticles into a graphene nanosheet-based nanocomposite influence the mechanical properties of the composite film. The figure below displays the Young's modulus and strength of finished composite films at varying percent weight of reduced graphene oxide film, RGOF, and then carbon nanomaterial. The graph shows that as the percent weight of RGOF and the carbon nanomaterial increases, the Young's modulus increases, but the strength peaked at 50% RGOF. This indicated that the more RGOF weight percent increase, the mechanical strength would also increase, but the material is brittle at high RGOF content. The purpose of the study is to create both strong and durable material. Therefore, the optimal composite of RGOF and carbon nanoparticles for the study would have been a 1-to-1 ratio of weight percent RGOF and carbon nanoparticles. Results also led to the key conclusion that the presence of hybrid nanoparticles demonstrated improved bridging, dispersion, and crack deflection, possibly affecting the interface detail of composites and the condensated state structure of the polymer matrix. In summary, hierarchical structures at different length scales, interface adhesion, and synergy of multiple toughening mechanisms are essential to the optimization of mechanical properties of graphene-based polymer nanocomposites. The manufacture of hierarchical structures like those in biocomposites remains challenging. Considerations of the synergistic effect between different nanoparticles must be made in addition to interface design to create an effective balance between strength and toughness. The mimicry of structural and interface features of bio-nanocomposites using synthetic composites presents great opportunities, but further research is needed to optimize the mechanical properties of these materials. Research in this study was very effective at conveying the influence of biomimicry on graphene nanosheet-based nanocomposites, but often skipped from example to example, making the purpose of some examples hard to relate to others in the section.